So as we have completed the interface flux in heat transfer, we would be starting with interface flux in mass transfer. Similar to interface flux in heat transfer, the interface flux in mass transfer equals to the total flux at the interface. Here we will consider a naphthalene plate of length L. The concentration of naphthalene at the wall is CaW. The component A is naphthalene and component B is air. Naphthalene A is diffusing in air B. C infinity is the concentration of naphthalene in bulk air and V infinity is its velocity. NaW is the flux at the wall. Rate of heat transfer equals to integration of the total molar flux over the entire surface area of the plate. The total molar flux equals to summation of the total flux at the interface, which is then equals to the molecular flux plus the convective flux. Molecular flux equals to quantity per unit volume or into mass transfer velocity. Here the quantity per unit volume is the concentration and velocity Vy star. The equation of rate of total molar flux becomes minus dCA by dy at y equals to 0 plus Ca into Vy star at y equals to 0. Minus dAb dCA upon dy is the fixed law of diffusion. Here dAb is the diffusivity of A in B. dCA by dy is the concentration gradient at the wall. Vy star, here Vy star cannot be assumed 0 because as per the no slip boundary condition, because as we assume Vy star equals to 0, Vy star is a function of Va and Vby in the y direction. If Vay equals to 0, then the total flux would be 0, which is not possible. So we would not consider Vy star equals to 0 as we have considered in heat transfer because of the boundary condition. So we will now integrate the total flux over the entire surface area of the plate, which gives us the rate of mass transfer of species A. At low mass transfer rate, the total flux at the interface becomes only the molecular flux, which is minus dAb dCA by dy. dCA by dy is very hard to estimate because of the complex nature of flow characteristic. To account for the experimental observations, we take the help of Newton's law of mass transfer or Slattery equation. According to Slattery equations, NaW equals to Kc CaW minus Ca infinity, where Kc is the mass transfer coefficient. So by substituting this Slattery equation 2 in equation 1, we will get small na equals to integration 0 to w integration 0 to L Kc CaW minus Ca infinity dx dz. By integration, after integration, we will get WL, which is the area, into Kc into CaW minus Ca infinity. So this expression is the rate of mass transfer, where Kc is the average heat transfer coefficient. We calculate Kc by integrating Kc over the entire surface of the plate upon area of the plate, which is WL. So the rate of mass transfer Na star becomes Am, which is the mass transfer area, average heat transfer coefficient, into the concentration difference delta C. So now let us look at the physical interpretation of mass transfer coefficient. Mass transfer coefficient is represent how easily species A moves from wall to the fluid through concentration boundary layer. By equating Slattery equation equals to fixed law of diffusion, we get mass transfer coefficient equals to dAb upon CaW minus Ca infinity dCA by dy. dCA by dy is hard to estimate because of complex nature of flow characteristic. In actual flows, the actual profile of the concentration is parabolic, but to make things simpler, we consider a linear concentration profile over the flat plate. The thickness of the stagnant film which forms on the flat plate is del C. But though the concentration difference or driving force is same in both the cases, which is Ca infinity minus CaW. dCA by dy then becomes Ca infinity minus CaW upon del C, which is the thickness of the stagnant film over the flat plate. By substituting dCA by dy in equation 1, we get Kc or mass transfer coefficient dAb upon del C, where dAb is the diffusivity of A in B and del C is the thickness of the stagnant film. So now let us look at how to calculate or evaluate CaW. CaW is the concentration at the interface or the wall. So as we have considered component A to be solid and component B to be fluid, fluid can be any, gas or liquid. So Ca infinity easy to know because it can be measured experimentally, but CaW cannot be measured experimentally or analytically. To calculate CaW, we have two options. If the fluid is gas, then the CaW is Pa saturation upon RT, where Pa saturation is the saturation pressure of the solid. We can calculate Pa saturation by Antony's equation. Antony's equation equals to ln Pa saturation A minus B upon T plus C. If the fluid is liquid, then we can simply calculate it by finding out the solubility of the solid in liquid at specific temperature.